So we've been working on these proof type problems where we're comparing two functions, and we've been using some consequences we've learned of the mean value theorem to do so. And in this video, I have another example for you, and I actually want to show you another method on how to do a proof for these types of problems. So why don't you pause the video and work on this guy here. Try to figure out if sine of x is greater than or less than x on this interval where x is ranging between 0 and pi over 2. All right, assuming that you've given it a go, I told you I wanted to show you another method, so we'll call this a first method, method 1, and this is the one we've been working with so far. And again, I'll state up front, this is my favorite method. And in order to do a proof for this problem, and we need to figure out, what it is sine of x greater than or less than x? We're going to find that out. And in order to do that, we're going to start our proof, and we are going to state that we have a function, g of x, and we're going to define this function, g of x, as sine of x minus x. We're going to bake in all of the information of our inequality. So sine of x minus x minus x. Okay, and again, we're looking for we're looking for x between 0 and pi over 2. Okay, and in order to do this, again, we want to look at a base point. We want to look at a g of 0 in this case, and that's going to be 0 minus 0, so that's 0. And what does this help us do? Well, again, we're trying to end up using a consequence of the mean value theorem. So we're going to next look at some derivative information, and based on the sign of our derivative in this interval here, we're then able to make a comparison between g of x and g of 0. And real quick, I forgot to mention, is g of x defined? Is it continuous, differentiable on this interval? Yes, it is. So we're able to talk about it and its derivative in the way we're about to. So our derivative, let's take the derivative. G prime of x is equal to the derivative of sine of x is cosine of x. All right. And then we have minus 1. So our derivative, we need to figure out on this interval where x is between 0 and pi over 2, is cosine of x greater than 1 or less than 1? We need to figure that out. And I think graphing it would be our best bet here. Graphing it would give us some nice intuition behind what's going on. So we have 1, and this could be pi over 2. All right. Cosine of x looks something like that. Something like that. Just imagine it lands at pi over 2. So y is equal to cosine of x, and x is between 0 and pi over 2. That's what we graphed here. Now the question is cosine of x less than 1 or greater than 1 on this interval between 0 and pi over 2? Well, it's less than 1. It's less than 1. The highest value it takes on is at x is equal to 0. And that's when cosine is 1. But all throughout this interval here, we are going to be less than 1. So therefore, our derivative on this interval here, since cosine is less than 1 on it, this is actually going to be negative. This is going to be negative. So then we are able to state this. We're able to say, therefore, by a consequence of the mean value theorem, since our derivative is negative, our function is decreasing on our interval, and therefore g of x is going to be less than g of 0. G of x is less than g of 0. So then all we need to do is backfill in our information. So let's do that. So we find the following. We have sine of x minus x, so minus x is going to be less than g of 0. And g of 0 we found to be 0. And again, that's for our interval. And then we just add over this x, and we have the following. We have that sine of x on our interval is actually going to be less than x. Is going to be less than x. And we can put a QED at the end to be demonstrated. So we have the following. We have sine of x is less than x. So that is what we find here. Now that we found this, I wanted to show you another method on how to go about these problems. So let's show you another method. Let's do that in yellow. Let's get some space. Not as much space as I wanted. That's all right. We'll say this is method 2. Now, the difference between these two methods that I'm going to show you, this first method here actually took some consequences from the mean value theorem in order to complete a proof. This second method here is actually going to manipulate the mean value theorem itself in order to prove this inequality. So here's what I mean by that. Let's just write out the mean value theorem. So we have f of b minus f of a over b minus a. And this is equal to f prime of c, and that c value is between a and b. And we have on our closed interval, our function is continuous. We're just writing out some of the qualifications to use the mean value theorem. And on our open interval, our function's differentiable. So that's the mean value theorem, and you've already seen this. But now I want to rewrite it. I want to rewrite it as this. Say that f of x minus f of 0 over x minus 0 is equal to f prime of c. And I'm saying that c now is between, c is going to be between 0 and pi over 0 and x, which is going to be less than pi over 2. So basically, if I were to translate these guys, it would be saying, okay, we are going to let b be equal to x, which x is ranging, but it's always going to be less than pi over 2. That's what's represented down here. And then we are letting a be equal to 0. So that's the translation between the two. Now that we have it in this form here, we are going to name this function. And we're going to name this function f of x is going to be equal to sine of x. All right? So if f of x is sine of x, then we can find the rest of this information here. We'll find f of 0 and our derivative evaluated at c. So f of 0, sine of 0 is just 0. And then taking our derivative, derivative of sine of x is cosine of x. Okay? And then we want to evaluate this at c. So this is cosine of c. So now we have all of our information. Let's plug that back in to this restatement of the mean value theorem. So we have the following. We have sine of x minus f of 0, which is just 0. So we won't even write that. And then we have over x, and this is equal to f prime of c, which we found to be cosine of c. And again, this c value is ranging between 0 and ultimately pi over 2. Okay? So that's what we have there. And let's multiply both sides by x. And we have a sine of x. Sine of x is equal to cosine of c times x. So that's what we have. And now here's kind of the crucial part of the proof of this method here. We need to figure out, is cosine of c on this interval where c is between 0 and pi over 2, is cosine of c greater than or less than 1 on this interval here? And we can look at our cosine graph here where we graphed it on this interval, and we can see that cosine is going to be definitely less than 1 on this interval. It's going to be less than 1. And why is that important? Because now we can compare. Cosine of c times x. We can compare that with x. And we know it's going to be less than x. Again, where c is ranging on this interval between 0 and pi over 2. And this is directly what we said, all right? Cosine of c is going to be less than 1, so something less than 1 times x is going to be less than that x value, again, when we're looking at this interval here between 0 and pi over 2. So that is the crucial part of this proof. And now, since cosine of c times x we said was equal to sine of x, we're able to say that sine of x is going to be less than x. And that is our proof. There we go. So we got the same answer. That's great. And again, you can see, I tried to tell you right off the bat, I liked method 1 a lot better. And I think method 2 is a little more involved. But if you like it, go ahead. I mean, it's just rearranging the mean value theorem in order to make this proof. And the other method, I think, is a little quicker and a little quicker to go through, and I think it makes more sense in my brain at least. But before you go, I wanted to give you a graph. So that is the graph of our two functions, and you can see that y is equal to x is greater than y is equal to sine of x on this